the folks watching this video were not born yet when the Voyagers launched, but surprisingly, the spunky spacecraft are still in service billions of miles away from the Earth. However, NASA's made an even more shocking announcement that the Voyager is on its way home. How is that possible, and what does it mean for space exploration? In this video, we dive into NASA's recent announcement that the Voyager is returning back to Earth. How far away from home have you ever gone? Were you glad to be back home? If you were the Voyager 1, you would have covered billions of miles in distance traveled. In fact, the Voyager 1 has traveled almost 15 billion miles into space, making it by far the farthest human-made object. It is the first spacecraft ever to travel out of the solar system and reach the region called interstellar space. The Voyager 1 has captured human attention for decades since it launched in 1977, but nobody could have imagined the mission would still be active and continue to return data almost 50 years later. The spacecraft entered interstellar space in August 2012, nearly 35 years after it began its journey. However, the discovery was not made public until 2013, when scientists had time to review the data returned by Voyager 1. Voyager 1 was the second of the twin spacecrafts to be launched, but it was the first to race between Jupiter and Saturn. For a generation, the images returned by Voyager 1 have been used in school books and by many media outlets. The spacecraft also carries a special record called the Golden Record, which is designed to transport voices and music from Earth into space. The Voyager missions took advantage of a rare alignment of the outer planets that occurs once every 176 years. This alignment enables spacecraft to slingshot from one planet to the next, making the best use of their limited fuel. NASA had planned to send 2 probes past Jupiter, Saturn, and Pluto, as well as 2 other probes past Jupiter, Uranus, and Neptune. Budgetary constraints forced NASA to scale back its plans, but the 2 Voyager spacecraft still accomplished a lot. Voyager 2 flew by Jupiter, Saturn, Uranus, and Neptune, while Voyager 1 stayed close to Jupiter and Saturn. Recognizing that the Voyagers would eventually travel to interstellar space, NASA authorized the production of 2 golden records, which would be placed on board the spacecraft. On board, sounds ranging from whale calls to Chuck Berry music. Hey, don't knock NASA's music taste until you try it, as well as spoken greetings in 55 languages were installed. The 12-inch wide gold-plated copper discs also included illustrations of how to use them and the location of our Sun among nearby pulsars, a type of fast-spinning stellar corpse known as a neutron star, in case extraterrestrials came across the spacecraft and wondered where they came from. Both spacecraft are powered by 3 radioisotope thermoelectric generators, which convert the heat produced by plutonium's radioactive decay into electricity. Both probes were outfitted with a total of 10 scientific instruments, including a 2-camera imaging system, multiple spectrometers, a magnetometer, and detectors for low-energy charged particles and high-energy cosmic rays. The Voyager's communications system has also been used by mission team members to study planets and moons, bringing the total number of scientific investigations on each craft to 11. Interestingly, Voyager 1 almost didn't get off the ground at its launch, as its rocket came within 3.5 seconds of running out of fuel. However, the probe made it to space safely and raced ahead of its twin after launch, passing beyond the main asteroid belt between Mars and Jupiter before Voyager 2. The first images of Jupiter were returned to Earth by Voyager 1 in April 1978, when the probe was 165 million miles, or 266 million kilometers away. Voyager 1 discovered a thin ring circling the giant planet, much to NASA's surprise. It also discovered 2 new moons, Thebe and Metis. Furthermore, Voyager 1 returned detailed images of Jupiter's major Galilean moons, Io, Europa, Ganymede, and Callisto, as well as Amalthea. The Voyager spacecraft, like the Pioneer spacecraft before it, discovered Jupiter's moons to be active worlds in their own right, and Voyager 1 discovered some fascinating facts about these natural satellites. Io's numerous volcanoes and mottled yellow-brown-orange surface, for example, demonstrated that moons, like planets, can have active interiors. Furthermore, Voyager 1 returned images of Europa that showed a relatively smooth surface broken up by lines, implying ice and possibly an ocean beneath. Subsequent observations and analyses have revealed that Europa most likely contains a massive subsurface ocean of liquid water, capable of supporting Earth-like life. Voyager 1 made its closest approach to Jupiter, coming within 174,000 miles or 280,000 kilometers of the turbulent cloud tops. The probe was then directed towards Saturn. Close-up images of Saturn were only available for about a year until 1980. The ringed planet like Jupiter proved to be full of surprises. The F-ring, a thin structure discovered only a year before by NASA's Pioneer 11 probe, was one of Voyager 1's targets. Prometheus and Pandora, two new moons discovered by Voyager's high-resolution camera, keep the icy material in the F-ring in a defined orbit. It also discovered Atlas and the G-ring, as well as images of several other Saturn moons. Titan, the solar system's second-largest moon after Jupiter's Ganymede, was a mystery to astronomers. Titan's close-up images reveal nothing but an orange haze, leading to years of speculation about what lay beneath. Humanity wouldn't find out until the mid-2000s, thanks to images captured from beneath the haze by the European Space Agency's Huygens atmospheric probe. The encounter with Saturn marked the end of Voyager 1's primary mission. The emphasis then shifted to tracking the 1,590-pound or 720-kilogram craft as it approached interstellar space. However, 2 decades before that, Voyager 1 captured one of the most iconic images in spaceflight history. On February 14, 1990, the probe turned back to Earth and captured the famous image of its home planet from 3.7 billion miles or 6 billion kilometers away, in which the Earth is depicted as a tiny dot suspended in a ray of sunlight in the photograph. That day, Voyager 1 took dozens of additional photos, including 5 other planets and the Sun, in a multi-stage solar system family portrait. The pale blue dot image, however, stands out, reminding us that the Earth is a tiny outpost of life in an incomprehensibly vast universe. Voyager 1 broke free from the heliosphere, the giant bubble of charged particles that the Sun blows around itself, in August 2012. The discovery was made public the following year in a study published by the journal Science. The findings were discovered after Voyager 1's plasma wave instrument recorded a powerful solar eruption between April 9th and May 22nd, 2013. Electrons near Voyager 1 vibrated as a result of the eruption. Researchers discovered from the oscillations that Voyager 1's surroundings had a higher density than what is found just inside the heliosphere. It appears contradictory that electron density is higher in interstellar space than in the vicinity of the Sun. However, researchers explain that the electron density at the heliosphere's edge is significantly lower than at Earth's surface. Researchers then went back through Voyager 1 data and determined the official departure date to be August 25, 2012. The date was determined not only by electron oscillations, but also by measurements of charged solar particles taken by the spacecraft. On that fateful day, the same day that famous Apollo 11 astronaut Neil Armstrong died, the probe detected a 1,000-fold decrease in these particles and a 9% increase in galactic cosmic rays, which originate outside the solar system. Voyager 1 was 11.25 billion miles or 18.11 billion kilometers from the Sun at the time, or about 121 astronomical units. Since entering interstellar space, Voyager 1 has returned a wealth of data about the conditions in this region of the universe. Its discoveries include demonstrating how charged particles from the Sun interact with those emitted by other stars. Engineers are still astounded by the spacecraft's capabilities. NASA, for example, announced in December 2017 that Voyager 1 successfully used its backup thrusters to orient itself to torque with Earth. The trajectory correction maneuver thrusters had not been used since Voyager 1's flyby of Saturn in November 1980. Since then, the spacecraft has primarily used its standard attitude control thrusters to swing it into the proper orientation for communication with Earth. But as the attitude control thrusters' performance deteriorated, NASA decided to test the TCM thrusters, which could extend Voyager 1's operational life. That test was eventually successful. And other measures have been taken by mission team members to extend the life of Voyager 1. To conserve Voyager 1's limited power supply, they turned off the spacecraft's cameras shortly after the pale blue dot photo was taken. The cameras wouldn't pick up much in their deep space darkness anyway. The mission team has also turned off 5 other scientific instruments over the years, leaving Voyager 1 with only 4 operational: the cosmic ray subsystem, the low-energy charged particles instrument, the magnetometer, and the plasma wave subsystem. This is the first time we've been able to directly study how a star, our Sun, interacts with particles and magnetic fields outside our heliosphere, assisting scientists in understanding the local neighborhood between the stars, challenging some theories about this region and providing critical information for future missions. The next major encounter for Voyager 1 will occur in 40,000 years, when the probe will pass within 1.7 light-years of the star AC plus 793888. The star is approximately 17.5 light-years away from Earth. Now, if the Voyager 1 is so far away, how does NASA manage to receive data from it? The spacecraft sends information and pictures back to Earth using the Deep Space Network, or DSN. The DSN is a collection of big radio antennas in different parts of the world. That is no mean feat, as it takes more than 20 hours for a signal to travel from the Earth to the spacecraft and vice versa. The radios on the Voyager spacecraft are 23 watts. This is more than the 3 watts used by a typical cell phone, but it's still a low-power transmitter in the grand scheme of things. Earth's big radio stations transmit at tens of thousands of watts and still fade out fairly quickly. The key to receiving the signals is thus not the radio's power, but a combination of 3 other factors: extremely large antennas, directional antennas that point directly at each other, and radio frequencies that are free of man-made interference. The antennas used by the Voyager spacecraft are massive. You've probably seen people with a large satellite dish antennas in their yards. These typically have a diameter of 2 or 3 meters. The Voyager spacecraft has a 3.7-meter diameter antenna that transmits to a 34-meter diameter antenna on Earth. The Voyager and Earth antennas are pointing directly at each other. When you compare your phone's stubby little omnidirectional antenna to a 34-meter directional antenna, you'll notice the main difference. The Voyager satellites are also transmitting in the 8 GHz range, where there is little interference. As a result, the Earth's antenna can use an extremely sensitive amplifier while still making sense of the faint signals it receives. And when the Earth antenna transmits back to the spacecraft, it uses extremely high power, tens of thousands of watts, to ensure that the message is received by the spacecraft. This is where the DSN comes in. When it comes to long-distance communications, NASA's DSN is hard to beat. It is the world's largest and most sensitive scientific telecommunications system. The DSN is NASA's international network of massive radio antennas that support interplanetary spacecraft missions, as well as some that orbit Earth. The DSN also provides radar and radio astronomy observations that help us better understand the solar system and the universe as a whole. NASA's Jet Propulsion Laboratory, JPL, operates the DSN, as well as many of the agency's interplanetary robotic space missions. The DSN is made up of 3 facilities located around the world that are equidistant from one another, about 120 degrees apart in longitude. These locations are in Goldstone, near Barstow, California, near Madrid, Spain, and near Canberra, Australia. The strategic placement of these sites allows for continuous communication with spacecraft as our planet rotates. Before a distant spacecraft sinks below the horizon at one DSN site, another site can pick up the signal and continue communicating. DSN antennas are an essential link for explorers venturing beyond Earth. They provide the critical link for commanding our spacecraft and receiving never-before-seen images and scientific data on Earth, propelling our understanding of the universe, our solar system, and ultimately, our place within it. For a few months each year, the distance between the Earth and Voyager 1 actually reduces, as if the spacecraft is returning to the Earth. Why is that? The answer is that for a few months each year, Earth's orbit moves closer to the spacecraft before moving away again. The Earth's orbit around the Sun is faster than the Voyager spacecraft's. The Earth travels through space at a speed of 67,000 miles per hour, or 30 kilometers per second. Voyager 1 travels at a speed of 38,210 miles per hour, or 17 kilometers per second. Voyager 2 travels at a speed of 35,000 miles per hour, or 15 kilometers per second. For a portion of the year, Earth orbits the Sun and accelerates toward the spacecraft faster than they can accelerate away. As a result, their distances from Earth are getting closer, albeit only temporarily. They never alter their outward movement. We are the ones who change. To illustrate, let's look at Voyager 2 since the same thing happens to it. Voyager 2 gets closer to Earth every year from late February to the beginning of June. Astronomical units, or AU, are used to measure the distance between objects in space. This measurement is based on the 1 AU distance between Earth and the Sun. The distance between Earth and Voyager 2 on February 20th, 2022 was 130.05518 AU, but the distance on February 22nd, 2022 was 130.05454 AU. Between these dates, Voyager 2 begins to approach Earth. But the story soon changes. On June 2nd, 2022, the distance was 129.72179 AU, while it became 129.72224 AU on June 4th, 2022. Between these dates, Voyager 2 resumes its journey away from Earth. But what is the long-term future of the Voyager spacecraft? The Voyagers will finally say goodbye to their solar system of origin when they pass through the Oort cloud, a shell of comets and icy rubble that orbits the Sun at a distance of up to 100,000 astronomical units, or 100,000 times the average Earth-Sun distance. At that point, the craft will begin to feel the gravitational pull of other stars more strongly than that of our own Sun the first time. It will take another 10,000 years for the spacecraft to approach an alien star, specifically a red dwarf star known as Ross 248. Scientists estimate that the flyby will take place about 30,000 years from now, though it may be a stretch to say the spacecraft will pass by that star. Now, the solar system and the Voyagers will have completed a full orbit around the Milky Way in 500 million years. It's impossible to predict what will have happened on Earth's surface by then, but it's a time span comparable to the formation and destruction of Pangaea and other supercontinents. The Voyager spacecraft will oscillate up and down throughout their galactic orbit, with Voyager 1 doing so more dramatically than its twin. According to these models, Voyager 1 will travel so far above the galaxy's main disk that it will only see stars with half the density that we do. What are the odds that Voyager 1 and the golden record on it will be destroyed in space? Well, the records were made to last, possibly for 1 billion years in space. Beneath the golden sheen is a protective aluminium casing, and beneath that, the engraved copper discs themselves. To truly understand how long these objects may survive, you must first understand the conditions they will be subjected to, which requires knowing where they will be. Scientists were particularly interested in how much time the spacecraft would spend engulfed in the Milky Way's vast clouds of interstellar dust, which they described as one of the few phenomena that could actually act to damage the spacecraft. It's a bleak scenario with dust pelting the Voyagers at a few miles or kilometers per second. The grains will act as a steady rain that slowly chips away at the skin of the spacecraft. When a dust grain only 1,000th of a millimeter across collides, it leaves a small vaporized crater. The vertical oscillations of Voyager 1 indicate that the spacecraft will spend more time above and below the plane of the galaxy where the clouds are thickest. Researchers ran thousands of simulations of the two spacecrafts' paths and encounters with dust clouds, simulating the damage the golden records would sustain along the way. This work also necessitates considering the possibility of a cloud's gravity tugging on one of the Voyager's trajectories. Because the clouds have so much mass concentrated in one place, they may act to bend the trajectory of the spacecraft and fling them into new orbits, sometimes much further out, sometimes even deeper into the galactic core. Because their engraved sides are tucked away against the spacecraft bodies, both golden records actually have a good chance of remaining legible. The outer surface of Voyager 1's record is more likely to erode away, whereas the information on Voyager 2's record is more likely to become illegible. The main reason for this is that the orbit that Voyager 2 is thrown into is more chaotic, making it much more difficult to predict with any certainty what kind of environment it will be flying through. But despite the onslaught and potential detours, both golden records are highly likely to survive at least partially intact for a span of over 5 billion years. Modeling is difficult after 5 billion years. That is when the Milky Way will collide with its massive neighbor, the Andromeda Galaxy, and things will become chaotic. The orderly spiral shape will be severely warped, if not completely destroyed. The Voyagers will be caught up in the merger, the details of which are difficult to predict so far in advance. Meanwhile, the virtual touristing continues. During this 5 billion year model-friendly period, each of the Voyagers will most likely visit a star other than our Sun within 150 times the distance between Earth and the Sun, or 3 times the distance between the Sun and Pluto at its most distant point. However, it's difficult to say which star that is. It might not even be a star we know today. While neither Voyager is likely to approach any star before the galaxies collide, the craft are likely to pass through the outskirts of some solar systems. What's strange is that it could be a system that doesn't yet exist, a star that hasn't yet been born. Such are the dangers of working on a billion-year timescale. The fate of the Voyagers will be determined by the terms of the galactic merger. The collision itself could propel a spacecraft out of the newly monstrous galaxy, a 1 in 5 chance, but it would remain trapped in the neighborhood. If that happens, collisions with high-energy cosmic rays and the odd molecule of hot gas will pose the greatest threat to the golden records. These impacts, however, will be far rarer than the dust that characterized their damage inside the Milky Way. The fate of the Voyagers within the combined galaxy will be determined by how much dust is left behind by the merger. This may be minimal because star formation and explosion both slow, reducing the amount of dust flung into the galaxy. Depending on their luck with this dust, the Voyagers may be able to cruise through a truly alien cosmos for trillions of years long after we are gone. Such a distant time is far beyond the point where stars have exhausted their fuel and star formation in the universe has ceased entirely. The Voyagers will be drifting through an unrecognizable galaxy devoid of so-called main sequence stars and populated almost entirely by black holes and stellar remnants, such as white dwarfs and neutron stars. No matter which way you look at it, it's a dark future. The only source of significant illumination in this epoch will be supernovae produced by the once-in-a-trillion-year collision of these stellar remnants that still populate the galaxy. Let's hear what you think about the Voyager spacecraft's future in the comments section below.